Thank you. All right. So after the introduction by Federico, I will focus on the manufacturing of metal powders and the characteristics of metal powders. And first of all, I will introduce one of the two dominating manufacturing methods for making iron and iron-based steel powders. The original method is referred to as sponge powder production. In this case, the raw material is actually iron ore, enriched iron ore that is mixed with coke and limestone, and is then reduced in a tunnel kiln furnace. The reduction takes place in the solid state, so there's no melting taking place. And after the first step of reduction, it's also necessary to have a secondary step of reduction to reduce remaining oxides, but also to reduce the carbon content of the iron powder. And the reason for doing this is to obtain a soft and compressible iron powder. The result is an iron powder particle that typically looks as illustrated with the image to the left here, a scanning electron microscope image. And as you can see, it's quite irregularly shaped. The cross-section light optical microscope image to the right here highlights the fact that inside the particles you also can find some porosity in the sponge iron powders. And the reason for this is, of course, that the material has never been molten. So it's a solid state reduction. And this will leave some pores inside the particles. The typical size range for the PM particles is up to 212 micron. And a large part of this, typically 15 to 30%, is actually below 45 micron. So the powders are in the micron range size-wise. The other and today more common manufacturing process for iron and steel powders is the water atomization process. In this case, the raw material is scrap, so it's a complete recycling of old steel. The scrap is molten in an electric arc furnace and further refined in a ladle furnace. And up to this stage, it's completely similar to conventional steel making. But instead of a continuous casting operation, the molten steel is poured through a tundish, and then the molten steel is split into billions of particles that are solidified very quickly thanks to high pressure water in big volumes. But and also after this process, there's a subsequent reduction annealing taking place to reduce oxides and further reduce carbon content to ensure soft compressible particles. And in this case, the typical shape of the powder particles is a little bit different. They are still a bit irregular, but more like a potato in shape because of the rapid solidification. But they are more regular than the sponge iron powder particles. And if you look at the cross sections here in the image to the right, the internal porosity is next to nothing. They're basically massive solid particles that come out of this process. The size range and size distribution for the water atomized iron powder is, however, similar to the sponge iron powder particles. Shape is different, but size and size distribution is quite similar. Now, one special feature with powder metallurgy is that we have more degrees of freedom when it comes to alloying methods. Of course, we can do what we refer to as prealloying, which means adding the alloy content in the melt, and this would then be the alloying method corresponding to conventional steel making. The advantages is that, of course, we have a very homogeneous microstructure because we have a chemically homogeneous composition of the powder. There is no segregation issue with any of the alloying elements because the alloying elements are in fact dissolved into the ion matrix. But this also comes with a couple of disadvantages. One is that it's rather difficult to make alloy changes. Also in our industry, we end up with rather standardized grades, standardized compositions, similar to the steel industry. But of course, one other impact is that due to solid solution hardening, the compressibility or softness, if you like, of the particles is not as good for the pre-alloyed powders as for non-alloyed powders or different alloying methods. One alternative alloying method is to use either a sponge-based powder or an atomized powder, and then to add mix alloying elements, for example, copper, molybdenum, or in some cases also nickel, and then actually run this through a furnace in a so-called diffusion annealing process. This means the alloying elements are diffused into the very surface layer of the particles. And this means we have no issue with the seriation because the alloying elements are actually physically part of the base powder, the base powder particles. But we maintain the higher compressibility of the base powder. So if we have a pure iron powder, the diffusion alloyed powder will have a similar compressibility or softness as the pure iron powder. But of course, also in this case, we cannot have an infinite amount of different compositions, so there will be a limited range of standard grades that we can offer using this alloying method. Of course, we have a third alternative, and that is, of course, to premix or admix alloying elements. This is commonly done with copper, for example. But of course, there is one alloying element we typically admix every time, and that's actually carbon in the form of graphite. Because to make sure that the base powder in the powder mix becoming a PM steel component is soft and can be compressed, pressed into a high density, as illustrated in the compaction process by Federico, then we have to make sure that these iron powder and steel powder particles are soft enough. And this is not the case if we have dissolved carbon in the steel. Carbon has a very high hardening effect. So we need to add the carbon in the shape of graphite. And then during the subsequent sintering process, then of course the carbon will diffuse into the iron and steel matrix to be completely evenly distributed in the final PM steel component, which then has a hardenability corresponding to the carbon content. So this is an important aspect to consider. If we look at the typical size ranges of PM powders and put them into some kind of perspective, then as mentioned, the PM powder is typically below 212 micron, with a fairly high amount in the -45 micron range. This is then a finer powder compared to coarse powders that are sometimes used for as addition in an ion source for welding electrodes, for example, and for some types of surface coating processes as well. If we look to finer powders, then we can find medium fine or fine powder would be very commonly used in metal injection molding. And also this fine powder is commonly used in many of the additive manufacturing processes on the market today. The ultra-fine powders and the nano powders are typically used in various surface coatings and surface layers for very specific use because they're fairly expensive to manufacture and also quite tricky to handle when they become as fine as this. This is typically not an issue with the PM powder. It's fairly easy to handle and manage. If we move on to the characterization of iron and metal powders, the powder characteristics, one such aspect which is important to determine is the size distribution. The individual particle sizes can be determined by, I think there are 13 different academic definitions of particle size. But luckily, in industrial practice, we only have to relate to 3 methods that are completely dominating for practical use. And we also have to bear in mind that we are not interested so much in individual particles. We are interested in the size distribution of a powder. And even a small amount of powder constitutes tens of thousands or hundreds of thousands, or in most cases millions or billions of powder particles. So individual particles are much less important than the size distribution of the particles. The most common method still, and the oldest method to determine size distribution, is a stack of sieves, where you pass through a powder sample through a stack of sieves with a coarser, a bigger opening at the top, and then finer and finer mesh openings in the stack of sieves from top to bottom. This is very easy to use, well established, and it's very easy to understand how it works. This method, however, is not so precise and also has a limited resolution. We cannot determine size distribution with very high precision using this method. And to complement this, then, a common method used is also laser diffraction. In this case, tens of thousands of particles pass through a laser beam, and the diffraction pattern behind the particles is measured, and this is then used to calculate the size of the particles and therefore also the size distribution. This is a good method that works quite well to determine size distribution for particles. A more recent method, which I think will become more and more common, of course, is image analysis, or to be more specific, dynamic image analysis, where the same kind of sample size as in laser diffraction is passing through a camera lens, and you take thousands of pictures and images, and based on the image analysis, it's also then possible to determine the size distribution of the particles, and in fact the size of individual particles in that case as well. For an atomized iron powder, for example, the size distribution is typically a normally distributed Gauss curve shape like this. But in the mixes we typically sell, where we have admixed graphite, perhaps copper powder, perhaps also a lubricant, then of course these added powders have a different size distribution than the base powder, the iron powder. And this means we will have a bimodal or even trimodal size distribution of the powder mix. And this will of course influence how this powder mix will behave when it's handled and used in industrial parts manufacturing. And this brings me to two very common standard methods that are used to determine key properties of a powder mix. One is highlighted here to the left, apparent density. The apparent density is the weight of a powder or powder mix passing through a standardized funnel into a cup with a defined volume. The ISO standard is 25 cubic centimeters of volume here. And by weighing then the weight or the mass of the powder inside, we can determine apparent density in gram per cubic centimeters. This will be influenced by the lubricant used in the mix. It will also be influenced by other additives in the mix, such as graphite or copper powders and so on. One disadvantage is that it's fairly operator sensitive. So if we ask 10 persons to do the same measurement on the same powder mix, we will see a scatter of measured apparent density as a result. And this is quite important to bear in mind. However, it's quite a good method to determine, to indicate what is required as filling depth in the cavity of the compaction tool in the press. So it's a good informative feature of the powder mix. The same equipment is used to also determine flow rate. In this case, a defined mass of powder or powder mix, 50 grams, is passing through the same funnel, and the time measured for these 50 grams to pass through is then measured. And if you have a photoelectric cell here that will take care of the timing, starting and stopping the timing, it's actually quite a robust method. And it's however, the flow rate as such, the time you measure, will be influenced by lubricant and other additives. And even though the method is more robust than apparent intensity, it's not necessarily a good indicator for the filling rate, how quickly you can fill the tool in the compaction process. It's an indicator, but it's not a very reliable indicator for this, which is important to bear in mind. A few other things that are very important to bear in mind when it comes to powder characteristics is segregation, because a powder mix is not like water. There are different types of segregation that can take place, and segregation means separation of different powder particles from each other. One is referred to as heap segregation, and this is what will happen if you have free-falling powder. Then you will see a tendency for the bigger particles to end up towards the sides of the heap, and the finer particles to be more concentrated in the middle. So free-falling powder is something that should be avoided in a PM part manufacturing plant. Another phenomena is percolation, and this is induced by vibration. If, for example, if you have a powder mix in a container and you transport this container using a forklift on the shop floor, you will see a tendency for the finer particles to trickle down between the bigger particles and end up at the bottom. If you've ever been transporting gravel to your home or a courtyard, you will see the same phenomena on the trailer when you empty the trailer, that you have a lot of fine particles at the very bottom, and this is the effect of the vibrations taking place. So you should not transport a powder mix in a container that is exposed to vibration. A third phenomena is air current segregation, and this is what actually happens when you have a powder mix filling the tool cavity, because of course in the compaction tool you have air, and then you fill this volume with the powder mix. And if it's a big volume, then of course you have a fair amount of air that has to leave the tool cavity simultaneously to the powder mix entering the tool cavity. Then you can get some of these air current segregation. And this will of course have a bigger impact to small, low density, low mass particles, such as the fine lubricant or fine graphite particles. They are more susceptible to this kind of segregation. So this is something to also consider. This can be counteracted by using a bonded mix where the finer low mass particles are organically bonded to the iron or steel powder particles. Another phenomenon is the so-called trajectory segregation. And this is if you have a horizontal transport of powder and it falls over a cliff, so to speak, or into a tool cavity, you will see a mass effect where the higher mass particles are thrown further than the low mass finer particles. This is something that will take place to some extent from the filling shoe passing over the tool cavity. However, this is normally not really a problem. It's only if you make very big size parts with quite a high fill depth, so you have a big tool cavity to fill in the compaction process, then this is something that will have to be considered. And again, organic bonded mix, where you bond the finer particles to the base powder particles, is an efficient way of counteracting this type of segregation. Now, speaking of segregation, one thing that is desirable is to have a homogeneous mix going into manufacturing of parts. But then we need to also consider what does homogeneous and heterogeneous mean. Well, homogeneity is actually defined as a condition where the lot or the batch has a situation where all elements of the lot are exactly identical. And then heterogeneity would be any state or condition deviating from this. And this actually means that in real life, you never find a truly homogeneous mix, meaning an ideal mix. those do not exist in reality. But that's not a problem in industrial parts making, and I will try to illustrate this on the final and last slide here. If you consider if this is, for example, iron powder particles, and this is, for example, copper powder particles, then if it looks like this, you can clearly see that you have iron to the left and copper to the right. So it's a binary system. It's not homogeneous. Then we can mix it a little, and then maybe it looks like this if we look through a cross section. We can still see we have a lot more copper to the right and a lot more iron than correspondingly to the left. So it's not homogeneous, but maybe in some cases it's enough. If we mix a little bit more, it looks like this. It's probably, we cannot easily see that we have a concentration of copper or iron to the left or right or top or bottom. So this is probably homogeneous enough. This will be good enough to make consistent sintered components. But to be truly homogeneous, it will have to look like this. It's a 50-50 binary system, then every second particle in horizontal direction and vertical direction, and also in the third dimension, which we cannot see on the two-dimensional slide, will have to be every second particle iron and every second particle copper. And I think you can easily imagine that even if we mix for a long time, this will never actually be the case. So homogeneous enough is really what we're aiming for and what we want to make sure we maintain when making the parts. So these are an introduction to the key features of powder characterization. If you have questions, you're more than welcome to get in touch with me or Federico, and I've put my email address here in case that would be of interest. Thank you. That was my final slide, so I will then stop sharing to leave the scene for my successor.